let's get into partial derivatives. Just a couple things I want to talk about conceptually, and then we're going to look at calculating them because we're going to be calculating a lot of partial derivatives, the remainder of the semester. And so just like with Calc 1 and Calc 2, you want to get the rules down so that those aren't holding you up as you learn new concepts. I'm going to skip the first couple of slides and just go right to the interpretations because we're not going to do partial derivatives using the limit definition, but it's conceptually the same limit definition you learned in Calc 1. What does this thing give us? Well, it still gives an instantaneous rate of change, just like in Calc 1, except now it gives it only in one direction. So you saw how there were two partial derivatives for a function of two variables, first order partials. There'd be 3 first order partials for a function of 3 variables. There'd be 10 first order partials for a function of 10 variables, so on and so forth. What that does is it calculates the rate of change in that direction, holding the other direction constant, right? And that is the key to partial derivatives, is if you're doing, let's say, f sub x, so the partial in the x direction, y is a constant to you. You treat it like a constant when you take your derivative, you treat it like a constant when you interpret it. We're specifically talking about the rate of change in the x direction, okay? Think of this in terms of real life. Let's say, we talked last time, the amount of money in a bank account depends on both interest rate and time, right? If we take the partial derivative with respect to time, we're looking at how our bank account is going to change with respect to time, if the instant rate stays constant. Vice versa, if we did the partial derivative with respect to rate, what we're looking at is how the bank account is changing as the rate changes, but we're holding time constant. All right, so that gives us a little way to start to ground what we're talking about. Graphically, it actually still gives a slope of a tangent. We'll look at some plots next time, but same thing. It gives us the slope of a tangent line in the x direction holding y constant, or y holding x constant. We have a couple different notations, and we have to be familiar with both so we know what we're being asked. So we can see, sorry, I'm looking for my stylus. Every time they come in here, they move stuff. That's what I was thinking. No. Oh, there it is. Okay. So we need to be familiar with both notations. I typically like the f sub x notation. Well, nothing of that. Gosh. But both are perfectly fine, and they both convey what we're looking at, right? F sub x means the partial with respect to x. So it's measuring the change in our output variable with respect to x, holding y constant. Same thing with f sub y. What you see on the lower part is if we want to evaluate these at a point.
Professor Clark.
Right? Screen sharing stopped for some reason.
Right. Yeah. All right. Cool. Thanks.
Okay. The ones on bottom are if we want to evaluate it at a point, right? If we're trying to find a tangent line or a tangent plane at a point, or an instantaneous rate at a point, we want to insert the point, and those are just the notations for it. Okay. Let's think about what we know about contour plots and figure out what the signs of our partials are at each point. Okay. This is going to start to get this exercise of moving in one direction. So let's start with point A. So at point A, remember it's instantaneous. Okay, there it is. All right, let's try this one more time. So f sub x at point A. What do you think? Positive, negative, or zero? And remember what that means, f sub x. That's talking about moving in the x direction. What, it's looking at a change in z with respect to a change in x. So what do you guys think? Positive, negative, zero, and y. Not the letter y, but the. Okay, yeah, negative makes sense. Now I didn't label the z, the level curves on here, but we have the 3D plot over here, right? Which tells us that as we go outward from the center, we're increasing. So if we were to move from A in the positive x direction, our z value would decrease. So we would expect f sub x to be negative at A. What about f sub y? Because at each point we have two possible partials. And remember, you got to be a little careful. It's actually zero. Not that Mark's thinking was wrong, but this is an instantaneous rate of change. And if you remember what we talked about when we talked about level curves, if we move in a direction tangent to a level curve, we have no change in height. And because it's instantaneous, because if I draw my line here, I can see that line starts at a lower z value and goes to a higher one. But we're specifically talking about at point A, and we're tangent to our level curve at point A. Let's try another one, because this takes a little bit of practice. Let's do B next. Now think about where B sits, right? B is at the bottom of this paraboloid. What do you think about the partials at B? And think about what you know about even just single variable calculus. Bottom or the minimum of that bowl. They end up both being zero. We have basically a critical point there. Oh. This one. All right. So what about point C? Let's start with f sub x. All right, that would be moving essentially in this direction, but again, we got to consider it instantaneous. Is the z value is increasing, decreasing, staying the same? So Carter said that the contour lines are getting closer, so he thinks it's increasing. They are getting closer, but that's not necessarily why it's increasing. We could say that it has an increasing rate, that the rate is increasing. We got to be real specific about what's going on here. So here's the thing, at C, if we move in the x direction, we are not moving in a direction tangent to the level curve. Is everybody okay with that? So there's no way this thing can be zero. Has to be, because we don't have a constant function. So it either has to be positive or negative. It is positive. Why are we saying positive? And Carter had said positive.
Gotcha.
What about f sub y at point C? You guys are getting better at this. Like I said, it just takes a little bit of practice. All right, one more. And like I said, if you guys have questions, let me know, because this really starts to get home this idea. Okay, we're not changing colors on this one, apparently. Point D, f sub x, what do you think? Remember, moving into positive. So we say positive, very good. Now, what about f sub y? Because this kind of brings us home and gets all the different possibilities. Imagine it's a little move in that vertical direction. Okay, like I said, this is just to start to wrap our heads around moving in one direction while holding the other constant. Any questions about these signs? Positive, negative? All right, then let's talk about taking some partial derivatives. Well, that works. Basically, and you saw this in the video, I'm not going to do these because these are on the worksheet. So I put some extra ones on here for me to do to get just to, so you guys can see some extra examples. So I'm going to try and write big. So let me know if you guys at home can't see. This is what we're going to practice today, and you're going to have the whole weekend to practice this concept. Thank you. Okay. We'll do that one here in a second. Can you guys at home see that okay? It's about as clear as I can get it. Do your best, I'll talk as I go. All right. First thing we're going to do is find the two first order partials. Okay. So f sub x, and I should put in the xy, but if you don't, it's not a big deal. Okay, here's the nice part. Anything that just has an x in it, Calc 1 business as usual. So if I'm doing the derivative of x to the fourth, it's my simple power rule, 4x cubed. Okay, now, next thing, if you've got what I call an interactive term, it's got an x and a y. Well, what is y to us right now? It's a constant, so you treat it like a constant. So this is a constant, this is a constant. What's the derivative of x? 1. So I just get minus 2y cubed. That's it. Okay, doesn't need a product rule or anything. It's not a product because only one of them is a variable.
So if it was like 2x squared y cubed, it would be 4x y cubed?
Yep.
Okay.
Remember, y is a constant, so 4y to the 10th is a constant. The derivative of a constant by itself is 0. F sub x is done. And you guys at home, if you have any questions, just shout them out. I'll hear you on the speaker. Let's do y. Now this guy's a constant, so the derivative of that is 0. So I go to the next term. Minus 2x is a constant. So I'm just taking the derivative of y cubed, which is 3y squared. I'm going to multiply the 3 by the 2. So I got minus 6x y squared. And then we just have a basic power rule. So plus 40 y to the 9. All right, let's do the second one, because the second one, I tried to pick a couple of different, let's show up well. Let's just keep it in black. There's one thing I want you to wanted to show you in this one, guys. There's too many examples for me to go through them all. We are just going to have to get our derivative rules down, but these are a couple that have a couple different things going on. All right. So if I want to do g of x, the y is a constant, x is my variable, but I do now have a product. So this will be a product rule. Okay. So I'm going to have to set up my product rule, which is x times, we'll do it in 2 steps so you guys can see it. The derivative with respect to x of e to the xy. Now we leave this part alone, e to the xy times the derivative of x. Okay. So that was left alone. Now this derivative is a chain rule. Y is a constant. Derivative of an exponential is itself times the derivative of its exponent. Here's an interesting question for you. What is the derivative of xy with respect to x?
Y.
Perfect. We know the derivative of x is 1, y is a constant. So that's the derivative of the exponent. And then we have plus e to the xy. Derivative of x is just 1. Don't need to write it if you don't want to. So product rule is still very much a possibility and something we have to keep an eye out for, but not because of x times y. It's when we have a function of x times a function of x or a function of y times a function of y. Now here's something that's going to work out real nice for us. This one's not nearly as long because we no longer need product rule. That x out front is now just a constant. So this is x e to the xy times the derivative of xy with respect to y, which is just another x. So x squared e to the xy. Questions about either of those? Partial derivatives, just like derivatives, they take practice. Okay, that's what we're going to spend most of our time doing today. I'm not going to be talking much more than I already have, just a couple of things. All right. We also have what are called second order partials. These are our second derivatives. For a function of two variables, there are 4 second order partials. All right, there's f sub xx. There's f sub yy, f sub xy, and f sub yx. If you, just like if you can do a first derivative, you can do a second derivative. If you can do a first order partial, you can do a second order partial. It's the same exact process. All right, so let's look at a couple of these. I'm going to go a little quicker because I think you're starting to get the idea and you've seen them in the videos, and I want to show you something else and give you guys time to work. So please ask questions if they come up. But let's find f sub xx. Okay, now the order is not important when it's the same letter, but when we do f sub xy, that means we do f sub x first and then y. So the order here tells us the order we're taking the partials in. Okay, there's only one term in terms of x. It's just 12x squared. We're done. That's it. Because the derivative of 2y cubed with respect to x is 0. All right, well, while I'm standing here, let's do f sub xy. Okay, now let's talk about what this means. That means we're doing the first order partial with respect to x. So we're doing this guy here, but this time we're doing it with respect to y, which would be what?
-6y squared.
Well, this is 0. It's derivative. I should say its derivative with respect to y is 0. Derivative with this with respect to y is -6y squared. All right. Tell me, what is f sub y? What is the second order partial? What is the of this guy with respect to y?
-12xy.
-12xy, because x is a constant. Love it.
It's 360y.
Perfect. That's it. Again, 2 things you need to be able to do partial derivative rules. You need your derivative rules from Calc 1, and you need to be able to look at the off variable or variables if it's a 3 variable function as constants. That's it. Okay, this time we'll do f sub yx, which is this guy. We go back to here. So now we're doing it with respect to x. So this term doesn't have an x, right? So its derivative is 0. So we only have to worry about this term.
-6y squared.
Why does that sound familiar?
Because they're
Look at that. That is going to happen on pretty much every function we encounter this semester. It's not 100% guaranteed for every single function because of certain discontinuities, but almost all functions and all the ones we're going to deal with in here, that'll always be the relationship. So you now have a way to check your partials. If your f sub xy does not equal your f sub yx, you made a mistake somewhere. Okay, we can say that with 100% certainty in here. I'm not gonna do the other one because you saw what I wanted you to see on there. I wanted you to see product rule and I wanted you to see chain rule. So we will do that because we know kind of what we're looking for. I'd rather save time for you guys to try some. But I wanted to get to here. Our mixed partials should always be equal. Okay. All right, so just a couple examples on top of the ones you already saw coming in. And last thing I want to mention, those are all going to be on the worksheet too. Mixed partials, we just said were equal. We did some of the second order partials. I want to talk a little bit about what's going on with the second order partials. We're not going to do a ton of this, but I just want to relate it back to what you learned in Calc 1. So the second order partials talk about how the rate of change is changing, just like the second derivative does as the first derivative. So f sub xx, if it's positive, we have concave up in the x direction. If it's negative, we would have concave down. Same thing goes for f sub yy. That'll be really useful next week when we start looking at the second derivative test for determining what type of critical points we have. Maxes and mins, right? Concave up makes a min. Concave down would make a max. And then if you got a mix, concave up, concave down, you get what we call a saddle, right? We're not going to have to memorize this, but I just want you to be familiar with that concept. And then we'll use that idea to look at the second derivative test. The mixed partials are a little bit trickier because what you're looking at is how the rate of change in the x direction changes as you're moving in the y direction, or vice versa if it's f sub yx. So it's not as useful of information as f sub xx and f sub yy. But what we'll find is we use all three second order partials in determining the second derivative test for multivariable calc. So we will need to be able to use those.
Can I ask something real quick?
Sure.
How did you get in the problem that you worked? How did you get the f sub y of x? I know they're equivalent, but I can see how you would get f x of y, but
I'm missing a square. Or no, I'm not. So we're going from this line up here, right?
uh-huh.
So we're doing the derivative of this guy with respect to x.
Yes.
So y is a constant. So this derivative of this is 0, so it goes away. Derivative of this with respect to x, well, the derivative of x is just 1, which leaves us with the minus 6y squared.
Oh, okay. Gotcha.
Other questions? Let's do some derivatives. So there's some really good ones on the worksheet. I'm going to be quiet for the folks online. Give me just a sec.